Yeah, what I want to look at next is, let's use rectangles again to approximate an area under y equals x squared from x equals 0 to x equals 1. So this is a very small little tiny area. If, well, if we look at it, maybe even expand it out a little bit. So here's y equals x squared. And let's expand it out here. Make one a little more spaced out than we usually do. We should go through 1, 1. So when I say the area under that curve, that's y equals x squared. What area am I talking about? I'm talking about the area between the curve and the x-axis. So it's this area that I want to approximate right here. Right? That little sort of semi-rectangular area. I mean, it's not because you got a curve on the one side there, but that's what we want to approximate using these rectangles. All right, so number one, let's approximate that area using R4. Using R4. Now the good news on this is I've actually got the function, and so that'll take some of the estimate thing out that we had, but I mean it's still an estimate. But well, let's draw it just to kind of give us a visual. Again, we'll expand this out a little bit. All right. So R4, we just talked about that. That would mean right-hand endpoints and 4 rectangles. And so first thing you usually do on computing these things is compute your delta x, which is your width. What's delta x here? B minus a over n. Well, I'm going from 0 to 1, so the b and the a, b is 1 and a is 0, so 1 minus 0. N is the number of rectangles, so I've got 4 rectangles, so I'm talking a 0.25 or quarter, however you want to write it, I guess, but 0.25 is our width. So I'm going to divvy up the x-axis into quarter units. 0.25. And so that area all right, so that area I'm approximating with R4, all right? So it's this, these 4 rectangles here. I want to just draw them out first thing. It's those 4 rectangles. They're a little off because they should be equal width, but anyway, that's, you get the idea. All right, now, our area then is approximately this R4. It's just the area of each one of those. Well, each one of them's quarter unit, so it's 0.25 times then the height. Well, that's what I was saying here. We cut out a little bit of our, you get this, I get this answer, because I actually have the function here. It's y equals x squared. So isn't the height going to be whatever the height is at 0.25, which I know the height at 0.25 would be 0.25 squared, right? So I just put that. That way. You with me there? Let's see where I get that. To get that height, I'm just plugging the x value that I'm at into the function, the x squared. All right? So then the second one is 0.25, still the same width, times the height there. Well, now I'm at 0.5, because I go a quarter more over from there. Then the height would be, instead I had to estimate what it is, that height is whatever 0.5 is squared, just plugging it into our function. And so we do that across the board. The next one would be 0.25. The next x value to be added would be 0.75. So it'd be 0.75 squared. Would be the height on that one. And then the last one would be 0.25 times 1 squared, which is 1, but 1 squared there, just a minute. Okay? So that's going to be our R4. So again, if you want to, you can factor off the 0.25 and just add up the those values. But all right, so let's see, 0.25. So just multiply these out, however you want to do it. I get 0.46875. Okay, that's my R4 estimate. All right. Well, let's do L4. So approximate this area using L4. Well, the deal on that is, instead of right-hand endpoints, L would be left-hand endpoints, right? And so I'd go up using different heights for each rectangle. So it's still 4, so I'd still have 0.25, 0.5, 0.75, and then 1. I'd still use those same values. But I'm using left-hand endpoints, and so my area is going to be approximately the first rectangle. All right, so an interesting thing happens on the first rectangle. I don't get any rectangle at all because I'm using left-hand endpoints. The height, well, I'm at 0, 0 for the height. So there's no height for that first one. So the first one is, yeah, it's 0.25 wide, but the height is 0. All right? Because the left-hand endpoint on this, we're at 0, 0. All right, so the second one, using left-hand endpoints, the second one I'd have, the height would be there. Well, the height is the function value at 0.25, so I'd have 0.25 times 0.25 squared. So that'd be the height, because I'm still dealing with the same function, y equals x squared. So the height there is 0.25 squared. The second one, when I have 0.5 squared for the height. And then, last but not least, the last one would be 0.25 wide, but the height would be the height at 0.75, which would be 0.75 squared. And so, that, what does that give me? Basically the same thing, except leave off the 1 there. 0.21875. All right. With me there? Is this okay? All right, now, let's note a couple of things. So, I drew the picture, and we can see here again clearly that the 0.46875, that's going to be an overestimate. So our true area, right here, if I call it A, is something less than that. This is an overestimate, right? I'm sorry, an underestimate because, yeah, you don't quite have all the area covered with our rectangles in the second case here. So here's what I'm saying. The true area is somewhere between these two. So that's not a whole lot of spread, but I mean, I'm only talking about overall one unit. But anyway, we've got it pretty good. It's somewhere between those two. Now, like I was saying before, more rectangles is better, right? So if I did the same thing and I doubled the number of rectangles or subintervals to 8, well, it turns out R8 is 0.398435, and L8 for this same area is 0.2734375. And just like before, the R8 would be an overestimate, the L8 would be an underestimate. So that narrows it down even further. Here it's about, what, a quarter between them. Here it's 0.12 between them. So, you know, we've narrowed it down even further. So that's what I'm saying. The more rectangles, and if you look at if you try drawing it, maybe I will here, you can kind of see, yeah, if I'm going to divide 0 to 1 into 8, let's see. Eight rectangles, so let me do the right-handed endpoint ones. Yeah, the little overages there, well, they're just smaller than they were. Yeah, so I've got smaller little pieces that are over. So that's the R8 right there, the picture representation of it. You got less overages. The little pieces are smaller. I mean, you got more of them, but they're individually, each one of them is a little bit smaller. So that's what happens. When you do more rectangles, you get either smaller overages or underages, is that a word? Than you would have with less rectangles, okay? Now, here's another interesting little thing. Actually, this idea is kind of what we're leading up to, is what we're going to, more and more rectangles. Yeah, it turns out the book has a nice, has nicely figured out. All right, so for this same area here, they put it in a little table. If we use in rectangles or subintervals, and they computed L sub n and R sub n for us, because these would be hard to do, especially without one. All right, so if I've got 10 rectangles, it turns out L sub n is 0.285, and R sub n is 0.385. So that's even better than the 8s, a little bit. Shrinking in closer there. All right, then the 50, they got 50 there. 0.3234. 0.3434. Little jump on there. So you got 50 rectangles. Ooh, we're pretty close there between them. All right, let me put the 100 in the 1,000. So I've got 100 rectangles. L sub n would be 0.32835, and it's 0.33835 for R sub n. Then for 1,000, well, that'd take a while to do by hand, do 1,000 rectangles, but they did it for us. It's 0.33283, and then 0.33383 for R sub n. Those are really close together, aren't they? So that's one thing we can note. But here's the other thing, and we could do it on either one of these. Do you see something going on? Remember we did tables and with those secant line slopes? Remember doing that way back? But remember what those tables with those secant line slopes did is they allowed me to figure out the tangent line slope, because those slopes usually went to a specific number. Can we see here something that's going on as far as the limit is concerned here too? These are, either side, take your pick, aren't these going to a specific number, it looks like? What are they going to? It looks like they're getting closer and closer to 0.33333 repeating. What is that? 1/3, right? That's 1/3. So it looks like either side of this, I mean, it doesn't matter. If you look at the limit of these going this way, it looks like it's 1/3. Now what does that tell me? Well, it's a little different, I guess, than the secant line slopes, because what's happening here? What am I doing with my values of n? They're getting larger and larger and larger. So I'm running n to infinity, basically. Which means infinitely many rectangles, or subintervals. So if I can do infinitely many subintervals, infinitely many rectangles, it looks like the area here, this stands for the area under the curve, these R sub n's and L sub n's. It looks like the area is going to 1/3, doesn't it? Well, that's the idea that we're not going to have to do these tables like this, because that, like I said, that'd get ridiculous to have to do those by hand to do 1,000 rectangles, but that's the idea. The more rectangles, the better. And if we could run it to infinity, the number of rectangles, we can figure this out for sure, okay, precisely. And that's kind of how it did. Remember I said on the first one, the 3 rectangle, kind of how you figure it out is where you get that true area. But there's a little more work to do before we get to that. All right. And in the book, they do have a table that shows, I don't know if do they show 1,000 rectangles? So if you look in this section here in the book that we started, got 5-1. Not 5. Way too far away. What about 4? Yeah, 297. You can really see they do it up to well, they did the 51. They showed this one in the book. You can see there the gaps are not very much for 50. R50 and L50, I mean, they're just little bitty. You're just looking at little bitty, not even that big, it's little bitty gaps. So it's not very much overage or underage if you're going with L's. But anyway, it's kind of a good visual to see that, yeah, we're getting pretty close with this 50, and 1,000 and 100 would even be better. So, all right. Okay. So that's where we're going. We won't have to do 1,000 rectangles, don't worry, but that's the idea, that the more rectangles we can get, the better. So if we can do infinitely many rectangles, that'd be even better, and we will at some point. All right, but let me do one more of these just as an example to get the procedure for this down a little bit. And let's estimate the area under f of x equals x to the 4th plus x squared from x equals 1 to x equals 3. First of all, using, number 1, using R5. using R5. Okay, so drawing the picture, graphing it does probably help us visualize it. So let me sketch the graph here. I may not draw out the rectangles, but for one thing, it's getting quite large at 3. It's off my screen anyway. That's 1's along about there, 2 is right about there, and 3, like I said, 3's off way up there. But here's, you don't necessarily have to draw all the rectangles. I mean, it helps maybe if you want to, but sometimes that's not maybe feasible. So let me just show you. All right, so I've got, first of all, I need to compute my width, delta x, because it's, not always, definitely not always the same. What's delta x in this case? Well, delta x is always b minus a over n. In this case, the b is 3, the a is 1, n's the number of rectangles, R5, so that would be 5 rectangles. So that's 2/5. And let's call it 0.4. Okay? Now, one thing, it gets, you can draw them out. I like sometimes just to write out my subintervals here, the x values for them. Yeah, we start at a, which I said that's the x of 0, but you start at a, which is 1. And then the x1, well, you just keep adding delta x's to get the subsequent x values. So x1 would be the 1 plus 0.4, so it would be 1.4. Just 1 plus the delta x 0.4. And then x2, whether you mark, you can mark it on this, but you don't have to. This is another alternative. So what would x2 be? Well, x2 is just taking the 1.4 and adding the delta x. So that's 1.8. So you're just adding delta x each time to get it. Then x3 is 2.2, x4 be 2.6, and then x5 be the last one, be 3. That's where we end up. Okay? All right, now, here's the next thing. All right, so now R5, our approximation, it's just the area of those rectangles with those endpoints. So I'm starting at 1, first one's at 1.4, so maybe I will draw that in just to kind of give us an idea, first of all, here. So the first one is, it's 0.4 width, and the height then this is the next, like I said, the height here, one representation of the height is, well, if I'm using right-hand endpoints, that height is the function value at 1.4. So let me just write it preliminarily like that. Isn't that going to be the height of the first one? It's whatever the function value is at this 1.4 value. All right. What about the second one? Well, the second one would be same width, but what is its height? Well, its height would be, using right-hand endpoints, it would be the one at 1.8. So it would be the function value at 1.8. And we mentioned this a little bit earlier. Yeah, those heights are just the function values at your endpoints. In this case, the right-hand endpoints. And if it's left-hand endpoints, we would use the left-hand endpoint function value at that. So they're all basically the same. It's 0.4 times the height, which is the function value at each of these subintervals, endpoints. So the next one would be 0.4 times 2.2. The next one would be 0.4 times f of 2.6. And then the last one be 0.4 times f of 3. With me there? So the function values, that's what gives me the heights. All right. Now, actually computing those heights, well, here's our function in this case, the expression for it, x to the fourth plus x squared. So when I actually do this function value, you know, you can do it, there's several ways you can do it. You can plug it in by hand, you can use the graph, because if you do the trace feature on the TIs anyway, I think the Casios have it too, but if you hit trace, then you can just plug in, you know, 1.4, and it'll give you the height that way. So either way, what I again would point out is 0.4 is on all of these, so we can factor that off, and we don't have to mess with multiplying each time by 0.4 if we don't want to. All right, so however you want to get it, like I said, you can do it by hand. And this would be 1.4 to the fourth plus 1.4 squared. That's what this is going to give me, but I'm just going to go, let's go trace 1.4. It gives me the height that's 5.8016. Then this one, 1.8, it'd be 1.8 to the fourth plus 1.8 squared, but the calculator, since I got it in here, that's 13.7376. 2.2, 28.2656. And 2.6, it's only giving me 4 places left. If you wanted more, I guess you'd have to look at a table or something. And then 3. So you see how we're getting all those? We're just getting the function value, whether you want to do it by hand or use the calculator, doesn't matter to me. Just get those values. And then we just add those all up, multiply them by 0.4. Or multiply each one of them by 0.4. I don't care there either, but it seems like it's easier, be quicker to me if you just do the 0.4 times the sum of all those. Okay, 5 point. And the other hard part is just entering them all in here. Okay, I think I got it. About 76.1. How many different places they want? Okay. All right, now. Number 2 here, let's do one more. This will be our last one. Number 2 for this, area from 1 to 3, f of x equals x to the fourth plus x squared. But number 2, let's do M5. All right, let me erase all this, but I'm going to leave the x of i's here. Because here's the thing on the m's. Midpoint. So I want to use midpoints, 5 rectangles. Or sub-m's. So it's basically, I'm using 5 rectangles just like I did on number 1, so I still have the same delta x. That didn't change. However, what changes is these values that I use to get my heights. I mean, it's still these same endpoints, except now I'm going to use midpoints instead of endpoints. Let me expand it out just a bit. So let's say there's 1 and there's 2. Okay. So 3, so forth. I want to use the midpoints. Well, A is 1, then x sub 1 is 1.4 here, okay? But that's not going to give me my height. Where I'm going to get my height is the midpoint between 1 and 1.4. So that's what I like to do, have this list out here and put the midpoints. Now, here's another notation for you. A midpoint, if I have an x sub I and then a bar, that means a midpoint. Pretty standard notation. So a little bar over an x sub 1 or x sub 2. That means the midpoint for the first one or the second one, whichever you're on. All right, so let's do the midpoints here first of all, and that'll help me with my actual computation here. So what is the first midpoint? Well, it'll be halfway between 1 and 1.4. That's 1.2. The second midpoint, will that be the halfway point between 1.4 and 1.8? 1.6. And you can do it that way, but notice something else here, little FYI also. Once I get the first one, the first midpoint, then the second midpoint, just add delta x. Remember delta x, I erased my delta x, but delta x was 0.4 here. You just, once you get the first one, to get the next midpoint, you just add the delta x. You don't have to compute there. You can, but another alternative here, 2.0 would be the third midpoint. The fourth midpoint would be 2.4. And then the fifth midpoint is, of course, 2.8. Okay? All right, so now that's going to give me whatever my function looks like. That's going to give me my height. I go up at that function value to get the height. So M5 is going to be 0.4, still delta x. It's still 0.4y. But the height is going to be whatever the function value is at 1.2, you see. And then the second one is still 0.4y, but the height is going to be the function value at 1.6. So I've changed my where I compute my function. You see that? So the third one, function value at 2.0, fourth one is function value at 2.4, and the last one is the function value at 2.8. So again, really, I don't have to do each one of those times 0.4, just bring it off 1. All right, so let's see, 1.2, go back to my function. Yeah, I mean, you can, again, do it by hand. It's 1.2 to the fourth, plus 1.2 squared, but put in your calculator, trace, table, do a table, that's fine too. It helps you out here. So this would be f of 1.2 is 3.5136. F of 1.6 next, 1.6, 9.1136, 2.0, be an easier at 16 plus 20. 2.4, 38, 0.9376, and then 2.8, the last one is 69.3056. So now I just have to enter all those in and multiply them by 0.4. We got it. I get 56.34. 34186. 56.34186. Okay? Any question?